Right guys, once we've done this topic, this marks half the content for Unit 1. So this is the end of what the exam board like to call 1A. And this should still be mostly a review of things from GCSE. And what we're looking at is balancing equations for the most part, and then combining it with some of the other things that we've done. So we've already talked about ionic compounds, and to help you identify ionic compounds and to combine them correctly, it's helpful to know some of the really common ions. And here you've got a table filled with loads of the most common ions, but the ones that I've put in red, these are the ones that you are expected to know. So they will never give you these four. You just need to be able to remember them. So it's ammonium, which is NH4 1+, nitrate, which is NO3 1-, hydroxide, which is OH-, and then sulfate, which is SO4 2-. So those are the ones you just need to memorise. Now, the other thing I do want to note on this table, which I'm going to move my face completely out of the way for a second, is that all the positive ions are referred to as cations, and the negative ions are referred to as anions. So you just need to remember that, because sometimes they may talk about cations and anions, and that's all they're referring to, whether they're positive or negative ions. It's got the word ion in it, so hopefully it should be really easy to remember. Okay, so I just want to do a little bit of practice at writing ionic formulae, so making sure we've got the right number of each thing on each side. So in your booklets you've got a little space to write down these common ions. So copper chloride, iron 2 oxide, magnesium carbonate, barium iodide, ammonium nitrate and calcium carbonate. And you can use that table of common ions that you've just seen to help you do so. Okay, so next up is writing chemical formulas. So writing down these chemical formulas for our ions, just in case we weren't sure, you write down the name, write down the formula for each ion, and then balance the charges so you end up with something neutral. This should just be a recap on what you've just done. It's just if you had any trouble, this should review it for you. So for instance, sodium sulfate, the ions are going to be Na+, and the sulfate ion, which is SO4 2-. We can see that we need 2 lots of the Na+, in order to balance out the 2-, so we end up with Na2SO4. Easy peasy. So I'm just going to whiz through these on the PowerPoint on this video, so pause it, give yourself a chance to think. All you need to do is try and think, what is this ion going to look like, and write down the formula. I'll put the name up, then I'll give you a little hint, then a big hint, then the answer. Okay, so it's just a few to give yourself a go at. You can do it on a whiteboard or a scrap piece of paper or anywhere in your booklet really. So lithium chloride is your first one. There's your hint. There's your really big hint. And there's the answer. Next one is iron 3 oxide. We'll just get rid of my face, we don't really need it anyway, do we? Iron 3 oxide. There's your hint. There's your big hint. And there's your formula. Copper sulfate. Little hint. Big hint. Formula. Zinc hydroxide. Little hint. Big hint. Answer. Notice where the brackets are in this one, because we've got 2 of the OH, so the 2 is for all of the OH, which is why I'm going to put the brackets in when we do this formula. If you didn't put the brackets there, it would be 1N, 1ZN, 1O, and 2 H's, which is clearly not what we've got here. Zinc nitrate. Again, don't forget to think about brackets. There's your formula. Aluminium oxide then. So if you could do those, you could do the hardest that the exam board is ever going to throw at you. So that's a little bit reassuring for you, hopefully. Right then, we now need to move on to chemical equations, which I know you will have seen before at GCSE. Just need to remember the 4 steps when it comes to writing a chemical equation. You write the reactants on the left-hand side, draw an arrow, write the products on the right-hand side, and then you balance the equation. When we say balance the equation, it means we're looking for the same number of each type of atom on both sides of the arrow. So let's just look at an example. If I've got one carbon atom and two oxygen atoms and they react together, hopefully we all know that we're going to end up with a total of 3 atoms in our product, and it's going to be CO2. So if I was going to write that out, I would go C plus O2 goes to CO2. I would check to see it's balanced by seeing I've got a C on the left hand side and 2 O's, and on the right hand side I've got a C and 2 O's. So it's balanced. You imagine it like being on a seesaw. That's a balanced equation, so I'm all good to go. So what about if I've got C plus Cl2, which goes to make CCl4? Is that balanced? Well, not really, because if we look, I've got 4 Cl's on this side and 2 on the other side. So I need to change something to make it balanced. If I added an extra 2 Cl's on the left-hand side, I'd show that by putting a big 2 at the front, it's now going to be balanced, because I've got the same number of each type of atom on both sides. Next up, we've got O2 plus S8 goes to SO2. Hopefully we recognise these as being covalent compounds that we've looked at before. Products, reactants, products, arrow. So let's just stick them on that seesaw. Hopefully we can see that we are clearly got too many sulfurs on the left-hand side. So that's going to be a problem. If we top them up, I've got 8 sulfurs on the left with 2 oxygens, 1 sulfur on the right with 2 oxygens. So I need more sulfur on the right-hand side. So that means I'm going to need 8 lots of SO2. So let's throw that on there. If I throw my 8 lots of SO2 on there, I've now got the right number of sulfurs, but I now have 16 oxygens, which is a little bit of a problem, because now I've just gone over the other way. So I need more oxygens, clearly. So I've got my S8, which is fine, but now I need to get up to 16 oxygens. So if I have 8 lots of the O2, with my S8, that will leave me exactly the right number. And I've got a lovely balanced equation and a very full seesaw. But that's all we do. Note, whenever I'm adding to each side, all I'm doing is adding full molecules on. I'm not adding little numbers in between, so I'm not adding extra atoms into my molecules. I'm adding full molecules. So have a go at this one on your own. I'll have a look at the answer when you've done it. We'll have a peek next session. So Ag plus S8 goes to Ag2S. So give it a best shot. Now there is another way to approach writing these down, and this is the way that I personally do it. So rather than trying to draw out that seesaw and drawing all those molecules, what I do is I look at the equation and then I list the atoms that are involved on each side. So we've got Mg's and we've got O's. Then, to balance, I just count up how many of each atoms are on each side. So I've got 1 Mg on the left, 1 Mg on the right, I've got 2 O's on the left, and 1 O on the right. So looking at that, I can see that they're not balanced. So now I add big numbers to make up any imbalance. So if I add 2 onto the right hand side, I now adjust my total over here, and I've now got 2 Mg's and 2 O's. So I'm still not balanced, so I need to add another big number on. So I need 2 lots of Mg, adjust my totals again. I've got 2 Mg on the left, 2 Mg on the right, 2 on the left, 2 O on the right. So now it's balanced. Easy peasy. It's really not that difficult. I think a lot of times people get themselves in a bit of a knot about these because they think they're really hard, but it's not that complicated. You just go up in whole numbers. You don't need to worry about any fractions or anything. Just stick whole numbers on until you get up to the right number on both sides. So you've got some examples to give a shot to in your booklets as well. And there's also some here for you to have a little look at and see what you can do with. Okay, again, we'll come back and look at these. Right then, next thing we need to know about when we're doing chemical equations are state symbols, and these are really easy. You just stick them on afterwards whenever you're doing an equation. So if I ask you to do a chemical equation with state symbols, all you do is you put in brackets whichever symbol describes the state that thing will be in at room temperature and pressure. So for instance, with H2, I hope we all know it would be gas, so we just put a little g in brackets. For the O2, it would be gas, so again, we put the G. CO2, also a gas. H2O would be liquid, and C, carbon, would be solid. The last one is AQ, which is aqueous, it's dissolved in water. They would tell you if it was going to be aqueous, so you wouldn't need to worry too much about that one. if they told you it was in a solution that had been, been dissolved into water in a solution, you know the symbol you need is AQ. So to help you know which state symbols to use, this is a colour-coded version of the periodic table. The things in blue will be gases at room temperature. The things in red are liquids at room temperature, and the yellows are solids. And don't worry about the grey ones. Basically, they don't exist long enough for us to really identify a state for them. Okay, so again, if you want to annotate your periodic table, so every time you look you remember it, it just goes into your brain a bit more. Obviously, you're going to need to learn it for the exam. Okay, we're getting there, folks. I know it's a long one. So, limiting reagent. So, whenever we do a chemical reaction, what we often don't do is weigh out exactly the right amount of both chemicals. We normally have one that we have lots of, and then one that we have slightly less of. So the one that we have in excess, it just means there's plenty of it, and the one that limits how much we can produce, we call our limiting reagent. So just to give you a visual on this, if you think these are my products, my reactants here, ice cream cones and ice cream, I can make with those reactants 3 products. I can make 3 ice cream cones. Here, I've only got 1 cone but 3 blobs of ice cream. Well, my limiting reagent is my ice cream cone, so I've only got 1 of it, and my ice cream is in excess. But it doesn't matter that my ice cream is in excess, because with only 1 cone, I can only make 1 ice cream cone. It's the same idea, but just with chemicals. So in this instance here, if we're burning carbon in oxygen, we have carbon plus O2 goes to CO2. If we have 2 moles of carbon and 3 moles of oxygen, I should wait to have a think, pause the video for a second. Which is the limiting reagent? Which one's in excess? And what is the maximum number of moles of carbon dioxide that could be formed? So, if I look at my equation, I can see that 1 mole of carbon reacts with 1 mole of oxygen to make 1 mole of CO2. So that means that the 2 moles of carbon are my limiting factor. My 3 moles of oxygen means that my oxygen is in excess. And since 1 mole of carbon makes 1 mole of CO2, I would make a maximum of 2 moles of CO2. So let's look at a slightly more complicated version. And in this case, we need to use some of the things we learnt way back when we were looking at MR and moles. So remember, mass equals MR times moles. If you need to, get your first booklet out and have a look. In this instance, we've got 4 grams of copper oxide powder is reacted with 3 grams of magnesium filings, which is the limiting reagent. Now from the equation, I can see I have 1 mole of copper oxide reacts with 1 mole of magnesium to make 1 mole of each product. Now just because I have a smaller mass of magnesium, that doesn't mean it's my limiting reagent, because it's about the number of moles of it that I have in that mass, because this is saying that 1 molecule reacts with 1 molecule, so I need to know how many molecules there are. So have a little go at it. See if you can work out how many molecules are copper oxide, how many of magnesium, so which is the limiting reagent. Again, we'll have a look at this one when I see you next. Right, the final thing we need to talk about is percentage yield. And to do percentage yield, we need to first of all work out what theoretical yield is. To remind you, we've talked about this before, but yield is just how much of your product you make. So the theoretical yield is, if it went perfectly, how much product would you make? And all we do is, again, look at this equation. I've already been talking about it. So here's an example. I've got chemical A reacts with 2 lots of chemical B to make chemical C. So here I'm making 1 mole of chemical C. I use 1 mole of chemical A and 2 moles of chemical B. So here, 1 mole of CaCO3 makes me 1 mole of CaO, which makes me 1 mole of CO2. So if I had 100 grams of CaCO3, the question is, how much CaO can I make? So first thing I do is get the MR of both compounds that I'm interested in. So it's 100 for CaCO3, which is very handy, and it's 56 for CaO. So, if you remember from the equation, I've said 1 mole of CaCO3 makes 1 mole of CaO. So that means that 100 grams of CaCO3 yields 56 grams of CaO. And I know that because the MR is 100, so that means that 1 mole has a mass of 100 grams. So 100 grams of this will make me 56 of this. And if I just had 50 grams of CaCO3, how much CaO would I make? Hopefully you've just said half, so that'll be 28 grams. So, once we know how to do the theoretical yield, we need to work out the percentage yield. And this is a really easy calculation. It's just a comparison of how much is produced in a reaction compared to how much should have been produced. So your percentage yield equals your actual yield divided by your theoretical yield times 100. So I've given you 3 questions there to have a go at, where I've given you theoretical yield and actual yield, and I've just asked you to calculate the percentage yield. I've just worded the last one a little bit differently, but it is exactly the same question. So give those 3 a shot. I think you should all be absolutely fine with them. Okay, last thing, very, very last slide, I promise. I know it's been a long one. We need to know why percentage yields are never actually going to be 100%. And there's a few reasons. It might be because the reaction is reversible, so it starts to go back to the reactants from the products. It might be because some of the product is lost when it's separated from the reactants. So if you think about when we were making our banana oil and we were using the separating funnel, some of your product could have been lost out the separating funnel. And sometimes unexpected reactions might be happening, so you might have a secondary reaction that you didn't plan for that's happening in your reaction vessel, which means you lose some of your product. So if you ever do get a percentage yield of 100%, I would be very, very cautious, and it will absolutely never be more than 100%. Okay, so that is it. So this is the first half of Unit 1 all done and dusted, and hopefully it hasn't been too terrible. Okay, I'll see you in class.